So, the model that we are discussing begins with a simple atomic potential. You can all plot the Coulomb minus 1 over r in your figures in your notebooks, and projected on one dimension it will have a range, it will have a domain from minus infinity to plus infinity, right, and you can have a bound electron with some negative energy which is trapped in this potential. Now, how can you ionize this? And there are various ionization mechanisms which are possible and which are of interest in for our discussion. The one that is of interest is multiphoton ionization, that the atom absorbs a large number of photons, and that is responsible. So, this is the non-Einstein multiphoton ionization. But then the electric field of the laser, being very strong, has a potential which cannot be completely ignored compared to the atomic potential. So, the electric field of the laser in one half of the cycle will be one way, and in the other half of the cycle it will go the other way. So, it is the first half of the cycle for which this figure is shown, and the net potential will be a sum of the two. The first is Coulombic, which is 1 over distance, and the second is similar to what you see in the Stark effect perturbation theory analysis, right. So, it is a combination of these two, and if you look in the small r region very close to the center, the Coulomb field will dominate, the Stark field will be not of much consequence. But if you go to large r distances, it is a laser field which will dominate, and the Coulomb field of the atomic potential will not be of much significance. So, that is the domain of strong field approximation, because that is where the laser field really becomes important and you need a different approximation scheme. But now we will talk about somewhat steep suppression of the barrier. So, essentially what this electric field is doing is to suppress the barrier. There is a barrier due to which the bound electron cannot escape the atomic region, but you can suppress it by the application of this electric field. Okay, this is what is sometimes called as field ionization. So, to effect field ionization you can suppress the barrier, and we will now talk about a steep suppression of the barrier. So, now you have got a steep suppression of the barrier to the point that over here you hit a point where the electron can actually escape the bound region. Okay. It might come out with practically no speed, okay, and the approximation that we are going to talk about will consider the escape speed of that electron to be 0 when it comes out, but that is enabled by suppressing the barrier just enough so that the electron can escape the bound regions. So, this is called OBI, over the barrier ionization, and you can actually determine this distance at which this would take place. You can actually determine it because that is where the two potentials will become equal. Okay. So, this is called OBI, over the barrier ionization. So, one ionization process we discussed is multiphoton ionization, then you have OBI, over the barrier ionization. And now you remember the previous figure in which you had the sinusoidal electric field vector, and it reached the maximum only in a narrow time interval. Outside that, it does not have enough amplitude to suppress the barrier to this point, but if it is in that window, it can suppress the barrier to this. So, if it has not suppressed the barrier sufficiently, what is going to happen? The electron obviously cannot escape. Okay, it can escape only when it is at the sinusoidal maximum in that very narrow time gap, and then it is immediately going to come down. Not only come down, it will hit a 0 and go to the negative maximum and then reverse the sign of interaction between the laser and the electron, right. So, many things are happening over here, and if it is slightly less than this. So, let me show that in a picture. Even if it is slightly less steep than what is required for over the barrier ionization, if it is even slightly less than that, then you have this blue figure over here. The effective potential will be like this. This is obviously not to scale, very exaggerated diagrams, very qualitative diagrams, but I hope that they convey the sense of the physics that is going on over here. And now you have a potential barrier through which an electron can tunnel through. So, this is tunneling ionization. So, there are 3 ionization mechanisms: the multiphoton ionization, the over the barrier ionization OBI, and TI, which is tunneling ionization, and these are, each of these 3 is different from the photoionization that we talk about in the Einstein experiment. So, sure enough, light is absorbed and the electron comes out, but it is not the same thing as the Einstein photoionization. Each of these 3 is different, and we need to find a mechanism to parameterize these 3, to find some sort of mechanism to say that, okay, this is the condition that should be satisfied so that tunneling ionization will take place, another condition will be satisfied so such that over the barrier ionization take place, and so on. So, this is the parameterization that we shall be attempting, and this is it is to be remembered that the laser electric vector is oscillating. This is happening very fast at the frequency of the incident laser, and the peak is only during a very narrow time interval, and not only that, in half a cycle it actually reverses. So, this is a brilliant paper which I would draw your attention to, a paper by Paul Corkum, who one might have expected to be one of the Nobel laureates this year, but as I am sure you know, only 3 persons can be awarded the Nobel Prize, and they decided that it must all go to experimentalists. Corkum has also done some very nice experiments, but this was his later work, and the work for which he is more famous is theory, which deprived him of a Nobel Prize. But it does not matter to those who work in this field, because certainly everybody refers to this paper. So, let us say the electric field of the laser is represented by this vector. Alpha is a measure of the polarization state. So, it is 0 for linearly polarized light and plus or minus 1 for circularly polarized light, and you can develop the formalism for different states. And if electron wave packet escapes, then it is going to interact with this electric field, and then you can ask what will be the position of this electron, what will be the velocity of this electron, what will be the kinetic energy of this electron, and all that analysis can be done almost using classical physics. You can practically use Newton's laws to do that, because the energies are so fast. So, the energy is very high, the velocities are quite high as they pick up. So, you can use classical physics, but of course, one should be using quantum mechanics, and there are features in quantum mechanics which classical physics cannot and does not produce. So, here if you do a classical treatment, you can derive these relations for position and velocity of the electron, and I will discuss this in some details in the next few slides. So, here let us begin with linearly polarized light. So, this is the expression for the electric vector of the incident laser, and you can write a classical equation of motion for this electric intensity times the charge will give you the force, and this is the relation that you get for from undergraduate classical mechanics for the acceleration, and you can integrate this to get the velocity. A constant of integration will pop up, right, and if you write this expression in atomic units in which E m can be put equal to 1, so it is just a matter of choice of units, then you see that when E0 by omega is of the order of 137, because the speed of light in atomic units is 137, it is 1 over alpha. This is of course not exact, but very close. This is the fine structure constant as we know it from Dirac theory. Now, when E0 by omega is of the order of 137, you notice that these speeds become relativistic. Okay. So, this is an important parameter E0 by omega, and if you integrate this one more time from the velocity, you get acceleration. No doubt you will get another constant of integration, and you will, the actual position will also depend on the velocity at time t0. We will take that into account. You get this position which goes as E0 by omega square. So, omega is the frequency, so it goes as lambda square, right, and obviously it will be different for lasers with different lambdas, with different wavelengths. So, it is very much laser dependent. The intensity goes as the square of the amplitude, and the powers that we are interested in are of the order of 10 to the 14, 10 to the 15 watts per square centimeter, but it will depend not only on the power but also on the wavelength, as you can see, because it goes as 1 over omega square. Now, if you estimate this amplitude, this position, it goes as far as 65 atomic units. That is very far. Okay, means look at the size of an atom. It is the order of a few atomic units, or 1 atomic unit or thereabout, or 2 or whatever, but it goes as much as 60 atomic units away from this. So, during this transit it picks up, it is interacting with this laser, a laser which is oscillating, whose electric field is oscillating. It is no more at its peak, but it has come down, it hits a 0, it even reverses, and as it reverses, the electron will reverse the direction, it will be drawn back. This is the second returning wave packet, the part 2 of the 3-step model, but it is picking up energy from the laser and it is gaining kinetic energy. So, when it comes back to the atom, it has a lot of excess kinetic energy than just the binding energy it had when it was inside the atom, and all that excess energy plus the binding energy which has been overcome is now available for emission, and when that electron is recaptured, all that energy is emitted as high harmonics, and the kinetic energy that it gains, and the quantity of much interest in this is what is called as the ponderomotive energy, which is a term which is not very commonly used in many undergraduate courses, at least in physics. So, it sounds to be a very mysterious term, which it is not. It is just the kinetic energy averaged over one cycle. So, it is a very simple term. All you have to do is to estimate half mv square over one cycle and determine its average. So, that is the ponderomotive energy, and this is an important thing. So, if you we got an expression for x dot on the previous slide. So, this is the velocity. If you ignore this term, then the pondermative energy, which is half mv square. Other things are constant, you can determine them for a specific laser which has been used over here. E, m and so on are constants which you can plug in appropriate units. The average of sine square omega t over one period is half, as you know from your calculations of the simple pendulum as well. And you can see that this pondermative energy is already even for an 800 nanometer laser, it is like 4 times the energy. So you get not only 4 times this energy, but you get hundreds of times depending on lasers and so on. So this is just a simple calculation which I showed for one. There is a lambda square scaling, you can get hundreds, even 1000 times the photon energies, which is what enables the high harmonic generation. So, yes. Yeah, you want to come to the microphone over here to ask your question?
So just one doubt, like
you
mentioned about the amplitude x being around 65 atomic units, does it mean that it's actually moving some, does the length of the travel of the electron when it's ejected from the atom?
Yes, it is.
So there might be other atoms around it. Won't that affect the electron?
Yeah, so you're right, it's a valid question, you can sit down. Essentially, what comes into play is complex dynamics between the escaping electron wave packet, and then of course there is a mean free path which depends on the pressure, temperature and many other factors in the vacuum chamber where the experiment is being carried out. But there will be a part, not everything will come back, some will, and we are talking about those parts which come back. So, but they go very far, gain a lot of energy and then become a part of the returning wave packet. But the complexity is even more, which I am about to come to. So you are right, many other things are happening, we are not talking about everything that is happening in the chamber, we are talking about the part of the wave packet which escapes and then gets back. Much larger. So 65 atomic units is a large distance compared to atomic dimensions, but not large compared to the mean free path of the particle. So most of them will actually come back. There may be a chance that one of them hits something else, that probability cannot be denied, but rather unlikely I would think. Am I right, Arvind? Yes. Okay, so here we are. So you have the tunneling ionization. There are some details which I am yet to mention, which are very significant and important in our discussion. So here is our relation for the acceleration, integrated you have for the velocity, and now if you assume that tunneling takes place at a time t0, okay. So t0 is the instant at which tunneling takes place, and at this speed the electron comes out, let us say with practically no speed, it is just out. It is going to gain speed and energy because of its interaction with the laser, that is a different thing, but when it comes out, okay, it comes out with practically 0 speed. So that helps us determine this constant of integration, because at t0 this solution, this term plus the constant of integration is equal to 0, that gives us the constant of integration for velocity, and now you have this relation for velocity inclusive of this constant of integration, which is plus E over. So these two terms look alike, but mind you there is a variable t here, whereas this is the tunneling ionization time t0, and of course there is a plus sign here, whereas there is a minus sign here, okay. So now you integrate this again to get the position. This is the one that we were talking about, which is up to 60 many atomic unit dimensions. and that involves a constant of integration. Its actual value will of course depend on this constant of integration, but we can determine this as well, and that is what I do on the next slide. So, here if I assume that the tunneling takes place practically at 0, because compared to 65, about 100 atomic units away, it does not matter whether it took place at half an atomic unit or less than that. So, x at t equal to at t0 I take to be 0, and that gives me the constant of integration for xci, and the rest of it is just plugging in the constants of integration into this, very simple. And there is a very nice talk by Paul Carcom himself on the YouTube, which I am sure you can find easily. I will strongly encourage you to watch it. He describes how this very simple classical physics explains the phenomenology of the 3-step model. So, this is the position now, and it has got these two terms which involve t0, and these two terms, the first two terms involve the variable time, solution valid at any time. And what we are interested in step 3 is that recombination of the wave packet which has escaped has turned around because of the reversal of the sign of the electric field. It comes back, and let us say if tunneling took place at time t0, the recombination takes place after a certain time. That time is tau. So, we can ask what will be the speeds and the velocities at time t0 plus tau. So, that is what we determine to get the quantumative energy. Okay. So, this is the x at t0 plus tau. So, all you do is to put this t and this t over here to t0 plus tau and do some trigonometric simplifications. So, I will not worry about that. I will show the result on the next slide. And what is happening is that after t0 plus tau, it comes back and recombines, which means that the x at t0 plus tau is again equal to 0. So, that is important because that is a signature of recombination. Okay. So, here you have the x at t0 plus tau. You can use some simple trigonometric relations. I will not go through these steps, which is high school mathematics, but insert these expansions for yourself and convince yourself that this is what you get. Strike out the constants which are unnecessary to simplify the terms. Okay. And when you do this very simple mathematics, you get this relation for the tangent of omega t0, and I will use this relation on my next slide, which is the one which is of importance to get the kinetic energy. So, to get the kinetic energy, we need the speeds. The kinetic energy is half mv square, so you need the speeds. So, you got the x, you got the speed is given by this, the velocity, and you need the velocity at t0 plus tau. Okay? That is where you want what the velocity will be. So, in the general expression for v at arbitrary time t, you put t equal to t0 plus tau, simplify, use the relation that we got on the previous slide, which is for tangent of omega t0, and it simplifies this to what you see at the bottom of the slide. It is very simple substitution. So, I will not spend any time discussing it, you can work it out very easily for yourself. And now you can get the kinetic energy, which is half mv square. This is the average per optical cycle, which is why the 1 over t is appearing over there. It is the average over one optical cycle. So, you got the v at time t0 plus tau on our previous slide. You put this expression over here to get the average of this quantity, these things come out as constants, and you need the average of what is these cosine terms and so on, which has got the time tau which is required for the wave packet to come back and recombine. So, there is nothing new on this slide yet, it is the same as that we had on the previous slide, it is a summary of the previous relations. And then I am using the expression for the quantumative energy which we had obtained a few slides earlier, and I find that you can scale this right hand side in terms of the quantumative energy, because this factor comes out, and then you can define the average kinetic energy per cycle in units of the quantumative energy. So, this is an important factor in which many aspects of high harmonic generation physics scales. So, which is why this is an important thing to learn and to be acquainted with. And now look at the 3-step model. When the escaped electron comes back, many things can happen. It can actually scatter elastically when it interacts the parent atom, which is now an ion. It can scatter elastically. It can also result in E2E scattering. You know that if an atom has got more than one electron, and if it is bombarded by a beam of electrons, the incident electron can knock out 2 electrons. This is usually called as E2E scattering. Sunil did some work on this, E2E scattering. And then the phenomenon which is of interest to us is the high harmonic generation, which is the recombination. Now what happens is that the electron now we must remember that it is not quite a classical particle, it is actually a wave packet. Okay, this is quantum mechanics, and we have to respect that. I mean, the classical model explains many things, but not everything. So the returning wave packet has got a transverse width, and the transverse width is an important factor in determining whether E2E scattering takes place or high harmonic generation takes place. So this is a matter of great details. Our focus in this course is the high harmonic generation. And now if you look at this probability per cycle per electron volt, then this has got a cutoff. This cutoff is when the electron energy occurs at 3.17, so that is not an exact number, it is very close to that. Some people even approximate it to 3.2, but 3.17 is the commonly accepted number, and that is the reason that the high harmonic generation photon will have an energy which goes as much as 3.17 times the quantumative energy plus the ionization potential. So that is the energy which comes out, and those are the blue or ultraviolet X-ray pulses which are generated. Now what we have discussed is the energy dynamics, okay, the energetics. We understand why higher order harmonics are generated. So the peak is reached twice in a cycle, once when the electric vector goes at the top, another once when it goes to the bottom. So everything adds up in multiples of 2 omega, it happens twice in a cycle. So the original frequency omega is augmented to omega plus 2 omega, that gives you 3 omega. Then the next 2 omega, it gets augmented to 3 omega plus 2 omega, which is 5 omega. So you keep getting these odd multiples of the original driving frequency. Now we understand the energies, how high harmonic photons are generated. They are lasers, they are attosecond pulses of lasers. So certain phase coherence has to be achieved, and we have to discuss that, which is what I will be doing now.
How is this distribution obtained? This velocity distribution?
I'm afraid you're going to have to read Paul Carcom's original paper for this. Okay, this is a very nice paper, 1993 paper, and this is the celebrated reference for this. But this figure is one of the few things in literature which really explains the 3.17 factor. I mean, if you want a satisfactory explanation of 3.17, I think one has to go to this paper. And so, so here we are. Now, I am coming toward the end of this class, and we will break for lunch after this. But before we close, I will just mention a few points which we will carry on into the next discussion. The electron wave packet is in the field of the electric potential because of the laser field. So, its canonical momentum is not just the kinetic momentum, it is the kinetic momentum plus the vector potential of the electromagnetic field, and this is the one which is conserved. Okay. So, because this is conserved, the canonical momentum at time t0 must be equal to at any other time. It is conserved, it is going to be the same at all times. And you know that initially the kinetic momentum, the subscript k is for kinetic. For canonical momentum I use the subscript c, and for kinetic momentum I use the subscript k. So, canonical momentum I have not used on this slide anywhere as yet, but the canonical momentum at t0 is 0, which is also what happens to the vector field potential. Okay. And that means that the drift momentum is equal to the vector potential at time t0. It is exactly that, it has to be exactly that, and this is an extremely important thing which really impacts the phase of the returning wave packet, because all that information is trapped in the moment at which tunneling takes place, and that maintains coherence, but I will discuss it after lunch, or if I may remind, after a light lunch. So, the t0, the instant at which tunneling takes place, it determines the photoelectron momentum and the kinetic energy. I am using the term photoelectron, but not in the Einstein sense. So, if you choose an electron momentum, okay, it calibrates into the instant of ionization on a sub-cycle resolution, okay, because this is happening only in a very sub-cycle of the driving laser. So, this is on the attosecond scale. So, that is where the frequency factoring is taking place. So, luckily this is my last slide. I think the battery is about to run out. So, this is my last slide. Good timing. So, you have this moment of escape which determines the kinetic energy and the momentum and the phase relationships, but I will be discussing it in details in the next class, which results in brimstalling radiation. Energy limit we have already discussed, but we will also discuss the phase relationships which are really important. So, thank you very much. We will break for lunch.